Hello, hello. Welcome to my channel. I am Ameya and we are discussing about control systems. Today we are going to discuss about the steady state error and the error constants. Now steady state error is the deflection or the dynamic accuracy of your system where system tries to reach the final value and there are some errors in the final value because of which or there are some factors which affects the accuracy of the system and you don't get the final value. So steady state error is a measure of accuracy. If you have very accurate system, that means error will be less, and this error will arise in the system because of the nature of inputs which are there in the system, type of a system, and the other non-linearities which are affected in the system because of static friction, maybe backlash, etc. Okay, so the steady state error equation is very simple. We basically try to derive the equation. So this is the normal system, basic system. There is a transfer function. E of s is the signal coming from this summing point. There is a unity feedback. Okay, and then you have output and input. So we have two equations. We have derived these equations earlier also. The output upon input is a transfer function, and for closed loop it will be given by g of s upon 1 plus g of s. H of s will be unity. Okay, and also we have seen C of s is basically the multiplication of error signal and the transfer function. And then when we substitute E of s, you get E of s upon R of s is equal to 1 plus G of s, and effectively you will get E of s is equal to R of s upon 1 plus G of s. Now from this what we understand is R of s represents your input, okay, and this G of s represents your type of a system, right? So your steady state error depends on input, type of a system, and many other factors which are non-linear, many other non-linearities which in your system like static friction and backlash, which is very difficult to control. But we can definitely control this input and output. Now to find the value of steady state error, what we basically do is we apply a final value theorem. Okay, so this final value theorem is basically the error is basically you get when time is infinity. So this final value theorem gives you to apply limits for time tending to 0. So ESS is the expression for steady state error, and you have limit time tending to infinity f of t or e of t, you can say. This is in time domain. So if we try to convert it into s domain, you will get limit s tends to 0 s into e of s. We will substitute this e of s, so you will get limit s tends to 0 r of s into s upon 1 plus g of s, and you can use these formulas to find the steady state error in your system. Okay, so we will just create a block around that. This is the formula we will be using for your steady state errors, to find steady state error in your system. Now let us understand how this type of input will affect on my system. Those types of inputs will give you the three types of constants. Okay, the position constant, velocity constants, and acceleration constants. Okay, so let us start with this position error constants, which is represented by Kp. Kp. Now what we do for this position error constants, how do we derive the equation for position error constants? It's very simple. First we assume that is unit step input, right? That is one type of input, and we substitute R of s is equal to 1 by s for unit step input. We have seen this. Now how this formula will change? ESS is equal to limit s tends to 0 s into r of s upon 1 plus g of s, and then we substitute 1 upon s here. So s into 1 upon s, 1 plus g of s, there is a limit sign I forget to write, but this will cancel out, s and s will cancel out, and what you get effectively is limit s tends to 0 1 upon 1 plus g of s. If we try to simplify this, what you get is 1 upon 1 plus limit s tends to 0 g of s. Okay, so you can just substitute all s to 0 and then you can find the value of this. So this value will keep on changing depending upon g of s, right? There will not be always 0, there will be some constant. So we replace that with kp. So for that you get a formula. ESS for Kp will be 1 upon 1 plus Kp. What is Kp? Kp is coming from this. So you can derive a formula for Kp, that is limit s tends to 0 s into g of s. And this is called a position error constant. Okay, so this is how you get the Kp value for your system for unit step input. Now what about the velocity error constants? You will derive similar equation for velocity error constant using unit ramp input. Okay, so what is the equation for unit ramp input? You will get r of s is equal to 1 upon s square. Okay, and then you have kv is represented by velocity error constant, and then you can substitute everything. What is the formula for E of s? E of s will be limit s tends to 0 s into r of s upon 1 plus g of s. You substitute this r of s into 1 upon s square upon 1 plus g of s. 1 s will get cancelled. There will be 1 upon s. You can multiply that 1 upon s in denominator, and finally what you get is 1 upon, this will be 0, right? S will be multiplied, s tends to 0. You get limit s tends to 0 s into g of s, and this will give you the constant value. This will change with respect to g of s. So you will get the final value as ESS error constant is equal to, for velocity, 1 upon kV. Okay, I think I have made mistake. This s is not there. Okay, so this is not there for first. So let me correct that. Limit s tends to 0 g of s. You will just have g of s for the position error constant, and for kV you will have the s into g of s. So kV formula will come to limit s tends to 0 s into g of s. Similarly, you will derive this acceleration error constants, which is Ka. I will use, say, blue color. Ka, which is your acceleration error constants, and you will get limit s tends to 0 s square into g of s, that is your acceleration error constants. So basically you have three error constants depending upon three input. First is your step input, second is your unit ramp input, and for acceleration you will use unit parabolic input. Okay, you will substitute r of s as 1 upon s cube, and you can derive the same thing which we have did earlier, ESS, and at the end you will get the answer ESS is equal to 1 upon Ka, and that Ka will have this value, limit s tends to 0 s square into g of s. Okay, this is a square. So this is how the error functions can be derived. So first we derived the final, using a final value theorem, we derived the error function. Error of my system, or steady state error specifically of my system, can be given by limit s tends to 0 s into r of s upon 1 plus g of s. So this r of s is input. So steady state error depends on input. So we have derived different functions for different inputs. So starting with the step input, you get the position error constant, that is Kp. For ramp input, you get velocity error constant, that is Kv. And for acceleration input, you will get Ka, which is parabolic input. For parabolic input, you get Ka, that is acceleration error constant. And the errors, which can be represented by ESS, is equal to 1 upon 1 plus Kp, ESS is equal to 1 upon Kv, and ESS is equal to 1 upon Ka. We will just highlight that for now. This one, then this one, and then this one. So these are the important points for error. And for error constants, you have the values of this. Kp is equal to limit s tends to 0 g of s, Kv is equal to limit s tends to 0 s into g of s, and you have Ka is equal to limit s tends to 0 s square into g of s. Okay. Now in coming video, what we will discuss is how this type of input will affect my system. Type of input will affect my error on my system. First, we have seen error constants depending upon type of input. Now we will be discussing about type of systems and how my error will affect on type of system in coming video. Okay, so this is what I want to discuss in this video. We will meet in the coming video for next video on steady state errors depending upon type of systems. So if you like this content, do subscribe my channel, share it with your friends, and also check various playlists which are available on my channel for control system, mechanical measurement, and industrial automation. Thank you for joining.